Hi everyone and welcome back to another new video of Basics of Electrical and Electronics Engineering, which is a subject for the first year K2 syllabus students. So in this video also we are going to continue with module 3 AC circuits, and in this video we will be covering, in the last video we have covered purely resistive circuits, and in today's video we are going to cover purely inductive circuit. So I hope you have gone through the previous video of resistive circuit. The same manner of derivation is used in this one also, or an analysis method is used in this circuit also. That means a purely inductive circuit. Okay, so let's move on to the second one, that is purely inductive circuit. In a purely inductive circuit, we are going to analyze what will be the voltage equation, current equation, and using that we can understand what is the phase difference between these two. And also we can understand what is the power value, power factor, all those things. Okay, so I am going to draw an inductor here instead of the resistor. This is the inductor value. And here you can see the voltage across the inductor can be represented as VL, and current through the inductor can be represented as IL. The voltage which is supplied to the inductor is sinusoidal voltage, which is V is equal to Vm sin omega t. Now, as we did in the previous case, first we are going to write the voltage equation, that means the voltage across the inductor. Then we will find out what is the current through the inductor, and using that idea we can compare and analyze this purely inductive circuit. So let's write the equation for the voltage across the inductor. What is the voltage across the inductor? It will be same as the input voltage V, which is equal to Vm sin omega t. Now you can see here what is the current. So before that I'm just putting this inside a box so that we can make a look into when we are comparing with the current equation. Okay, let's move on to the current equation. How can we find out the current equation? You have studied in the plus 2 classes regarding the electromagnetic induction, in which E is equal to L di by dt, where L is the inductance of the inductor. Di by dt shows the change in the current. Okay. Now this E itself, or induced EMF itself, can be represented as voltage here. Why? Because the induced voltage across the inductor will be equal to L into di by dt. Now from this expression only we are going to derive what is the current. So for this purpose I am going to keep di by dt on that side itself. Okay. And taking VL divided by capital L, that means the inductance value. Now for keeping current alone or making current alone, we can write small letter VL divided by capital letter VL into dt. Now what is VL? VL is same as this input voltage, that is Vm sin omega t. I am just substituting it here. So Vm sin omega t divided by L into dt. Why? Because this dt is taken this side, that is di. Now our aim is to find out what is the current. So the current equation can be found out by integrating on both sides. So we can write integrating on both sides. Integrating on both sides, we will get integral di. No limits are there. Just we are integrating. Vm by L is a constant, taking it outside. Now the remaining thing is integral of sin omega t dt. You have to note here that the variable here for integration is t alone, which means omega has to be considered as a constant here. Now you have to remember the equation for integral sin at dt. What is the integral of sin at dt? It is equal to minus cos at divided by a, isn't it? So the same concept is used here, minus cos omega t divided by omega. Okay, so that will be your integral value, and integrating on the left hand side you will get the current value I. So I is equal to again Vm by L into this omega is also constant. So taking it outside and the remaining term is minus cos omega t. Now you just check this expression. Can you compare the current equation? So this is the current equation, correct? Can you compare these two? No, before that one more thing we can change is, you can see Vm is a constant, L into omega is also a constant. So these constants can be together made into another constant which is Im. So Im into minus cos omega t is the equation now. Still, can we compare this equation and voltage equation? No. Why? Because the cos, it is in cos omega t and this one is in sin omega t. If it is in sine form only, we can compare. So, I am going to convert this cos omega t into a sin omega t form. Just like this, you can see minus cos omega t can be written as sin of omega t minus pi by 2. You can just try to expand this one like sin A minus B. You can try this in a rough work as a rough work and you can find that it will be equal to minus of cos omega t. Okay, so this is the equation for representing the current equation. Now we can just put this inside a box. Why? Because we got the equation for the current through the inductor, which will be equal to Im sin omega t minus pi by 2. Now, I just told that Vm divided by L omega, all these terms are constants. So, and this can be called as Im. So, Im is equal to Vm divided by L omega, correct? Now, this, what is this L omega? Just like in the previous case, Vm by R shows the opposition for the current. Here, who is the opposition? It is done by L into omega. So, we can say that, just a minute, we can say that the impedance of this circuit, okay, impedance of this circuit is equal to L omega. Okay, what is this L omega? Have you studied this term? We will call it also as inductive reactance, that is XL. And this omega can be represented as 2 pi f. So we can also write it as 2 pi f into L. Okay. So impedance here, I'm going to represent the impedance as, in this particular case, the impedance is equal to inductive reactance is equal to inductive reactance. And what is the expression for inductive reactance? Which is equal to L omega, which is equal to 2 pi f into L. All these are used for representing the inductive reactance. So next we are going to study, I hope you understood the concept of impedance and inductive reactance properly. Inductive reactance is equal to L omega is equal to 2 pi f and this becomes the opposition for the current. Okay. Next we are moving on to the phase difference between these two. So what is the phase difference between the voltage and the current? Just by looking at the equations itself, you can understand that voltage is on the zero reference axis and current is actually lagging just by looking at the equation. So I am going to write it as phi is equal to pi by 2 degrees lagging or minus pi by 2, which means actually it is pi by 2 lagging. So I am just representing here as lagging to understand that the angle is lagging one. And we have to write it here. Current lags the voltage by 5 degrees. And if we are changing the reference, if we are considering voltage current as the reference, then voltage will be leading the current by an angle 5 degrees. And what is the angle 5 degree here? That is pi by 2. Okay. So next we are going to write what is the power factor. What is the power factor here? Power factor is equal to cos phi. Cos phi here is cos of yes, pi by 2, cos of minus pi by 2, which is equal to 0. So power factor for a purely inductive circuit is equal to 0. So next we are going to find what is the instantaneous value of power. Sorry, before that we have to draw the phasor diagram. Okay, so let's try to draw the phasor diagram. We know how to represent a waveform which is lagging. So using the same idea we are going to use, or we are going to draw the phasor diagram here. Here you can see this is the voltage phasor. Voltage phasor can be represented as Vm sin omega t here. Okay. And the phasor is represented on the 0 axis like this. Next I am going to mark the current waveform. So the current waveform is actually lagging the voltage phasor waveform by pi by 2 degree, which means this is pi by 2, correct? By pi by 2, which means it is lagging the voltage by pi by 2, means your waveform will exactly look like this. At the middle of each point, when one is reaching 0, the other one will reach the peak value. When this one reaches its 0 value, it will reach its peak value, going like this. Okay, so this is the current equation. I is equal to Im sine of omega t minus pi by 2. Now let's represent the same thing in a phasor diagram. In phasor diagram, if we are plotting a waveform which is lagging the reference, we will represent it under the reference axis. So how much angle it is being lagging? You can see it is pi by 2 degrees lagging. So I'll represent the current waveform in a phasor diagram like this. I hope you understood the concept of how to draw the phasor diagram. So next we are moving on to what is the instantaneous value. How can we find the instantaneous value of, let's find out what is the instantaneous value of power. Right, instantaneous power. Instantaneous power, small letter p, is represented as voltage into current. Voltage across the inductor into current through the inductor. That is the small letter p, that is the instantaneous power. We understood that now we are having two equations. Across the inductor, the voltage is VL, which is equal to Vm sine omega t, and the current equation we just found out, that is IL is equal to Im sine omega t minus pi by 2. So I am going to write it as Im into sine of omega t minus pi by 2. And here I am again changing back the sine omega t minus pi by 2 into minus cos omega t form. See, for this purpose, for current to make into sine form, we converted minus cos omega t to sine omega t minus pi by 2. The same thing is being reversed. That means I am going to represent this sine omega t as minus of cos omega t. Okay, this becomes our equation. Now from this again I am going to make a small change. I am going to write this one as sine, minus is taken outside. So my sine 2 omega t divided by 2. Now how this is done is, we have studied that sine 2a is equal to 2 sine a cos a. Or if we have to represent only sine a cos a, then how will we write? Sine a cos a is equal to sine 2a divided by 2. The same concept is used here. Here sine omega t into cos omega t, minus is taken outside, can be also written as sine 2 omega t divided by 2. So this is the equation for the instantaneous power. Hope everyone understood. Next we are going to find what is the average power. So in the previous case we have already found out the average power first by plotting the waveform. The same thing we are going to do here. So first I am going to plot the two waveforms. That is, first one is the voltage waveform here. This is the voltage waveform. Next I will plot the current as well as the power in the same curve. Okay. So here you can see I am going to mark the current waveform, which is lagging exactly 90 degree, which means pi by 2 radians from the voltage. Okay. as we have already done in the previous case, what I'm going to do is to find the average power. First, I'm going to mark all the intersecting points with a dark color. And I'm going to split it into different intervals. So for this purpose, I'm going to take the green color and I'm going to make it as intervals like this. Okay. And we will check what is the value of voltage and current in each of these intervals. See here, this is the red color shows the current waveform. Next, we are going to draw the power waveform. So let's check the first interval. Before that, let's mark which are these values. This one is pi by 2, isn't it? Pi by 2, pi, this one is 2 pi. So this one will be 3 pi by 2. Now, let's mark the power curve in the first interval. That means in this interval from 0 till pi by 2. Just check what are the values of voltage, whether it is positive or negative, as well as the current, and multiply both. Here you can see voltage is taking the positive values during this time period and current is taking negative values during this time period. From 0 till pi by 2. Power is actually the multiplication of voltage and current. So positive value into positive value, positive value of voltage into negative value of current will give you an answer negative. Which means your curve will look almost like this, not perfect. But still it is a negative curve that you can identify just by considering what is the value of voltage and current. Next, we are going to analyze this interval pi by 2 to pi, and you can understand that voltage is positive, current is also positive. Together it will make a positive power. Why? Because multiplying positive into positive, you will get again a positive power. Now again you can see here the intervals are same. I have drawn it little bit wrong. You can see here the area under this curve and this curve will be same. Now again if you are analyzing like this, you will get a curve like this. Positive values into negative values gives a negative power. Okay. And going on like this, you will get a curve like this. Okay. So next we are going to find what is the average power using this concept. So for this I am going to draw the power curve alone so that you can easily find out what is the average power. Okay. So I am just marking the power curve alone. So the power curve is looking like this. Sorry. Only one cycle I am going to mark. Okay. This much is pi and this much is pi by 2. The area will be same. Why? Because the intervals are same. So the area will be also same. So this is the power curve. Just by looking at the curve itself, we can understand that it is a symmetrical one. And what is the power equation, instantaneous power equation? That is to be written on this side, that is small letter p, which is equal to, we have already found out the equation, that is minus Vm into Im into sine 2 omega t whole divided by 2, or Vm Im by 2 sine 2 omega t by, okay, sine 2 omega t, that's enough. So this is the curve equation. Now we have to find the average power. So just by looking at the curve itself, you can understand that the positive area and the negative area are actually equal, and the average power will be equal to 0 as it is a symmetrical one. Okay. Now we are going to prove this one, that is the average power in a purely inductive circuit is equal to 0. So for proving this, we know what is the equation for finding the average power. Area under one cycle divided by time period for one cycle will give you the average power, correct? So what is the average power? Area under one curve means integral 0 to pi we have to take. Okay, equation is P into d omega t whole divided by pi. Why? Because that is for one cycle. Now we are going to substitute the equation here. Now only substitution is there. Minus Vm Im by 2 sine 2 omega t is the equation for P, and d omega t here whole divided by pi. You can take the constants outside. So here your equation becomes, now we can take the constants outside. So you will be getting the expression as Vm Im by 2 pi minus is here integral 0 to pi sine 2 omega t d omega t, which means only 2 becomes a constant here, sine 8t dt. Okay, so 2 only is the constant there. So again I am writing the same thing, Vm Im by 2 pi integrating sine 2 omega t, you will be getting as cos 2 minus cos 2 omega t whole divided by 2 in the intervals 0 to pi. You can take this negative sign outside. So negative into negative becomes positive. So your equation becomes Vm Im by 2 pi. Instead of this 2, we can take it again inside. So 2 into 2, your answer becomes 4. So 4 pi. Okay. You can see here Vm Im by 4 pi. Then we can substitute the upper limit and lower limit, which means cos 2 pi minus cos 0. Okay, let's substitute the values of cos 2 pi and cos 0. You will get it as cos 2 pi is 1 itself. So 1 minus 1 is equal to 0. Or now we have proved that the average power for a purely inductive circuit is equal to 0. So this is what we wanted to prove. One more thing I forgot to mention, average power, or another name for this one is active power. Now let's just find out what are the 3 important powers which we have to study here. The first one is apparent power. What is the equation for apparent power? Apparent power is equal to Vrms into Irms. Next one is active power. Active power equation is Vrms Irms cos phi. Here, what is cos phi here? Cos of pi by 2 or minus pi by 2, which is equal to 0 here. Or we can say the active power in a purely inductive circuit is 0. So next one is reactive power. Reactive power equation is Vrms Irms sin phi. Sine of minus pi by 2 is 1. So your answer is Vrms Irms into 1, which is equal to Vrms into Irms. I hope you understood how we can derive or we can analyze a purely inductive circuit. So everybody study well. Thank you everyone for listening. Stay tuned for the next video. Bye.